It's time, so hello everyone once again, and thank you for joining today's webinar. Climate Change Can Extreme Value Theory Predict the End of Times, hosted by the IAA General Insurance Forum. I'm Ryutaro Yamada, Group Chief Actuary of MS&AD Group and Chair of the General Insurance Forum. I will be moderating today's session. Climate change has become increasingly tangible in recent years, yet much uncertainty remains. Today's presentation will offer insights into how we can assess future impacts of the climate change using the generalized Pareto distribution and explore when climate patterns may become unpredictable. We are pleased to welcome our presenters, Eric Dalmoro, Head of Pricing at Signal Iduna Re and former Chair of the Astin Board until 2024. Professor Stefan Loisel, Chair Professor of Actuarial Science and Risk at CNAM, Paris. Stefan is Associate Editor of IME and CAP Risks and co-editor of EAJ. His research covers climate change and insurance, ruin theory, Solvency II, regulation, ERM, and longevity risk. He holds SARA and the scientific director of the French SARA program with multiple awards for his PhD and papers. Before we begin, a few housekeeping notes. Yes. So audio is muted during the session, but we encourage you to submit your questions and comments via the Q&A icon at the bottom of your screen. We will address them during the Q&A session after the presentation. A recording of this webinar and the presentation materials will be available on the IEA website within the next day or so. Please visit www.actuaries.org and navigate to News and Events, Past Events Library. A quick disclaimer as usual. Next slide, yes. The views expressed today are those of the presenters and do not necessarily reflect the policies or positions of the IAA or the presenters. Neither the IAA nor the presenters provide any warranty and disclaim any liability for loss or damage resulting from the use of the information shared. With that, Eric and Stefan, the floor is yours.
Okay, thank you, Yamada-san. So maybe, and I'll stay on that slide to begin with, but maybe an introduction to about the genesis of this presentation. Actually, in May 2024, there was a meeting of the General Insurance Forum in Seoul, South Korea. And actually, I mean, Stefan, you were there, Yamada-san, you were there. You may remember we had an excellent presentation from Raid Muslin about climate change, and the question came, which was, yeah, okay, but how could we eventually estimate the impact of climate change on, say, pricing for insurance or reinsurance product? And actually, Stefan, I still remember that you said, yeah, well, the tail of say property risk distribution will be affected by any new cat which will happen with time, and each time your alpha the Pareto alpha, if you use a Pareto distribution, may decrease. And then yeah, I was like, that's a good idea, let's try it. And actually today, this is what you're going to see, how this Pareto alpha is evolving with time. And based on a certain database. Okay, now if I want to be clear, if you are depressed or you have eco-anxiety, you may not want to stay because actually we mostly have bad news. Sorry to say that. So really, if you don't feel good and you don't want to have any bad news, you'd better leave. Okay, the good news, on the contrary, is that after this presentation, you may see that there are some ways to maybe quantitatively integrate climate change in the pricings nowadays. So that's what we're going to do to present today. Okay, but before going into the, say, technical part and the quantitative part, maybe a few things about how you may feel about climate change. The first thing I want to say is that this morning, by the way, I was watching France 24, a French television, and it said in one of the comments that it seems that in the past 10 years in Switzerland, I'm based in Switzerland, by the way. So in the past 10 years in Switzerland, a quarter of the volume of the glaciers has disappeared. So that's one element that you may feel. Another one, and I'm going to go through a few elements that you may have seen in the past. So in 2021, I still remember that there was a heat dome in Canada, which was really unexpected. For me, Canada, that's more the land of ice hockey and cold temperatures, but here there was really very high temperatures, and these temperatures had impact on insurance in agricultural property, and that was very new for Canada. If you are in the US, you certainly remember earlier this year in January that because of drought in LA, in Los Angeles, there was huge losses due to wildfires, which destroyed a large part of Los Angeles. So that's, and again, the high temperature in January. Yes, in January, that was really unusual. If we go to Australia, again, the same thing happened back in 2019, huge temperatures, which were unusual. And finally, South America also had to suffer some heat waves. And I remember in 2022 in Brazil, there was a huge drought, and 57% of the soybean production was disappeared, was not there. So yeah, we have, just as an example of extreme events, they happened, but actually after you will see the presentation, you may think it may just be the beginning of further heat waves, further heat domes, etc. If we look at NatCat history, and that's the economic damages from storms, it's not very clear that there is a trend, but actually, yes, in 2005, we had Hurricane Katrina and Wilma. And by the way, Hurricane Katrina and Wilma back at the time, and if you are old enough, it had the impact of changing the calibration of the, say, commercial CAT models like RMS, CAT rate of our Touchstone Ray now, and EquiCat. And funny enough, at that time I was in Zurich Insurance, and the review of the CAT models had an impact on the capital requirement, which in turn had an impact on the pricing of life insurance. It looks strange, but this is really what happened. And I can tell you that the life insurance underwriters were really unhappy about that. And in 2017, it's more close to us, and Hurricane Harvey, Maria, Irma are really extreme events that happen. So that was for a small introduction. Now, Stefan, before we go into technical elements, you may want to mention a few things to keep in mind.
Absolutely, yes. Thank you, Eric. Good afternoon, good morning, or good evening to everyone. So before we go to this analysis and to try to determine when this end of times could occur. There are some caveats and some things to keep in mind. So I try to list the main things to keep in mind in one slide, but there would be more of them, of course. The first thing is that currently in many continents, the NatCat risk is being reassessed. There was a consultation recently in the European Union by EIOPA about the increase of solvency capital requirement for NatCat and the potential inclusion of new perils or new perils in new regions. And we've seen in many countries prices of NatCat risk to go up. I think there's a very big technical difficulty if we want to use extreme value theory for really extreme events. It's the problem of tail risks reassessment. So I worked with that with a former PhD student, Alexandre Mornay, who did a PhD thesis with Allianz France more than 10 years ago. And when we tried to estimate the return period of Lothar and Martin, which are two storms that occurred in the end of 1999 in France and partly in Germany, well, if you try to estimate the return period with classical methods before the event with the data of the insurance company at that time, you would probably find a return period around 150 or 120 years. But if you reuse the same technique after the big event has occurred, maybe in 2005, then the return period drops to 60 or 70 years, already in absence of any climate change consideration. So this means that because rare events are rare by nature, everything will be reassessed after a big shock. And in opposite to, I would say, classical risk, when you really deal with extreme risks, you have to accept some kind of strong adjustments because that's the nature of extreme events. One particularity of this Lothar and Martin cluster is that they occurred as a cluster of events. And of course, things that Eric will present in a few minutes could look a bit different if you group events in clusters or if you just consider individual events, even if they are grouped in a cluster, or if you aggregate everything over 1 year or over 1 month or over one region. So that's something that needs also to be kept in mind. Another issue is about as-if claim amounts. It's not always easy to determine how much one event would cost if it occurred today and not 20, 30, or 40 years ago. Not only due to inflation, but also due to the change in exposure and accumulation of wealth in different regions, as well as the impact of human activity and human construction. For example, we saw that for the Valencia floods, where the fact that many things had been built around a river made the event bigger. Another point concerns climate cycles. There are many climate cycles on Earth, and some events may occur, like some events that Eric mentioned, for example, in Brazil recently, because of the coincidence of the peak of several cycles at the same time. And therefore, there might be some other events which could look much more severe or much less severe if randomly one of the cycles happened to be somehow at its peak at the same time or slightly after. There's also question marks about human intervention for some floods, for example, in the Middle East. At some point, people wondered whether some rockets had been sent into the sky to get some rain, and whether it was the cause or the primary cause or an amplifier of some floods. Even if this was discarded officially after that, more and more natural disasters could be maybe worsened by human intervention, triggered by human intervention, which would lead to trials at the court. And very often they are also badly handled. This was particularly the case for the Valencia floods, where the signal had been given early in the morning, but then some authorities told everybody to be not to worry, and this caused many fatalities and many more casualties at the end of the day. A more statistical point is about the parameters of the generalized Pareto distribution. We will focus on this presentation mostly on the alpha, or this power of X at the tail probability to overshoot the level X. But in fact, the scale parameter might be also important. And when you try to do the estimation on some real-world data sets, very often you have several possibilities with very different value of scale and alpha parameters. There's also a question mark about is it possible to have infinite mean? Is the world finite? What happens after you destroy 100 times the total amount of wealth on Earth? And this has been always, even in actual research conferences, a real source of dispute between researchers. Some colleagues, for example, try to approach loss distributions with mixtures of Erlangs or mixtures of light tail distributions, because they think that they have to do it only up to a certain level of several billion US dollar, whereas other colleagues think that it's very dangerous, because these tails of mixture of Erlangs will die out very quickly, and it's preferable to stick to Pareto distributions. But in that case, in some cases, we get an infinite mean model. Does it mean that insurance or risk sharing becomes totally impossible? I will show you some literature review in the next slides, but in my opinion, this will mainly depend on how we implement collectively prevention and management actions in a very, very uncertain world, this uncertainty is not going to help us. And I concur with what Eric said at the beginning of this presentation. One of the key takeaways that I took from Red Musulin feedback after COP in the Emirates when he came back to the GI forum last May was that we should see Earth as a system, and we human beings and actuaries are part of this system, fortunately or unfortunately, for the management of natural disasters. So if we go to the next slide, how is end of times represented in actuarial and green finance literature? The first way is to say that, okay, we can have, let's say, to simplify, Pareto type loss distributions with alpha less or equal to 1, which means that in that case, we have an infinite mean. but our real or random variables are still always finite, almost surely. The second possibility is to have infinite mean due to a positive probability to have an infinite claim amount, for example, for nuclear accidents. The third way is to start from finite mean claim amounts and to get closer and closer to infinite mean, or to transition to infinite mean. This is basically what we're going to discuss with Eric during the end of this presentation. And I will explain what I had done with some colleagues some years ago. And another important aspect is that when you discuss with climate scientists, they would approach this notion as a notion of tipping point. We all witnessed tipping points, for example, if you like scuba diving. After you reach a certain temperature, the coral reef is dying. And this is a kind of point of no return. Maybe it will come back, but after a very, very long time. And some tipping points are at risk at the global level. I will show you a bit more details in the next slides. So on the next slide, I show you an excerpt of a very recent paper by Alfred Müller, who is a specialist, a colleague from Germany, an academic colleague specialist of stochastic orderings and risk sharing. And in this working paper, you can see already some references to a paper by Offert and Wüthrich already in 2012 about infinite mean Pareto models related to this nuclear power accidents risk. Elling and Wirfs in 2019 also worked on that for cyber risk. And Neshleova, Embrecht, and others also implemented some infinite mean models for operational risk in finance. And I remember some actuarial conferences where Paul Embrecht was saying that operational risk data in finance corresponded to the most extreme data sets that he had seen in his life in many, many fields. So it's not new to have this very infinite mean risks, but the question that we're going to discuss is, will it soon be the case also of Nat Cat risk? And if I just stay on the previous slide, sorry, Eric, thanks for just a few more seconds. Why is it also important from a risk-sharing point of view? You see here this equation 1 on Alfred Müller's paper. X1 stands for one risk, and you see that basically having one risk is better. So the risk will be smaller in the sense of the stochastic order compared to a kind of shared version of a multiple risk or a diversification of the risk. So when we switch to a world where we look like infinite mean, or where we have Pareto distributions with alpha less than 1, well, very often we're going to have a completely counterintuitive phenomenon, because one of the most important properties of our profession, diversification, will in that case fail in many cases. And Alfred Müller, if you are interested, related this the violation of this diversification effect to so-called super Cauchy distributions. Cauchy distributions, if you forgot your probability classes, correspond to stable distributions. So stable distributions means that if you if you combine, if you add independent copies of one random variable in some class, you remain in the same class. Probably the most famous one is Gaussian distribution, of course. But in the more general class of stable distributions, you have the Cauchy distribution, which is of infinite mean, even if it looks like a Gaussian distribution in terms of the shape, but the tails are too thick for the average to exist. So when I say that it's infinite mean, the positive part is infinite mean because the average is not even defined. So if I go to the next slide, I will now discuss how with Dominique Korczak and Pierre Ribeiro, we somehow had a look at this question between those two parameters that we mentioned. Okay, so if you see on the second line, you have this f bar t of x. X is omitted, but it's a survival function of a random loss. And you see that it behaves like a power of x, okay, 1 plus x divided by dt to the power minus alpha t. And so this means that we assume that as time t increases, where the loss distribution is going to evolve, and we assume that it's going to worsen due to climate change or due to something else. And there are two ways we could worsen the risk. We could play on the parameter alpha. In that case, it would be alpha of t and d would remain constant. Or we could play on d, which becomes d of t, and we leave alpha constant. And we're going to compare the two situations in terms of the impact on asymptotic ruin probabilities. So in a classical compound Poisson model, where simply we have some worsening of claim amounts due to climate change. Of course, it would be interesting also to include some increase of the frequency of claims, okay, but this would be another paper. And here we make a very big assumption. We assume that we are able to adjust the premium instantaneously, which is of course a very a much unrealistic assumption, and that we are able to maintain positive safety loading equal to rho. So what we're going to do, if you look at equation 1, is that we're going to say, okay, due to climate change, the average loss distribution increases by some percentage every year. And we're going to compare the situation where it's due to alpha and the situation where it's due to d, still respecting this same worsening of the average. So on the next slide, you see the result for you see the two models, okay? So we start with an alpha that is larger than 1, so we are in the finite mean domain. And if you look at the formula of alpha of t, you see that this is something that will start at some level alpha 0, which is larger than 1, and it will go to 1 in a decreasing manner without reaching 1. So we will remain each time on the finite mean mode, but we will get closer and closer to this kind of end of times that we had in the title. And the second option is to keep the alpha 0 fixed, but to simply have an affine formula for the parameter d, which becomes d times 1 plus c alpha t. So if we compare now on the next slide the results that we have, the intuition would be that maybe Eric, if you can move the zoom, yes, just yeah, thanks, perfect. So if we compare the two models, remember model 1 is when we have worsening due to the parameter alpha, and the model 2 is due to the parameter d. After some mathematics, we can get the following equivalent asymptotics when the initial capital U is large enough. And you can see that basically we compare something that behaves like a constant number times power U to the power minus 0.5 with another equivalent that behaves like a constant number times U to the power minus alpha 0 minus 1 divided by 2. And in fact, this means that if you start with a model where alpha 0 is larger than 2, for example, this means that you have a finite variance. In that case, it's more severe in terms of risk to worsen the parameter alpha. But it's not always the case. If you start from alpha equals, let's say, 1.3, in that case, it's worse to play with parameter d. So this shows that when we're in this domain close to the end of times, or actuarial intuition or extreme value intuition does not necessarily behave like we thought. And to conclude, I will just conclude on the next slide with the tipping points that are very important and could correspond somehow to the concept of end of times. So I show you two versions. The one on the left is by the Potsdam Institute of Climate Research and based on a paper published in Science, while the one on the right is based on the paper by Stephen and co-authors in Nature a bit earlier. And in those two versions, you see that some of the key phenomena that maintain somehow the climate of our world in a kind of equilibrium, or at least in an equilibrium with cycles, well, they are jeopardized by temperature increase in the range of +1 to +3 degrees, or in the range of +3 to +5 degrees, or on the left-hand side from the range +2 to 3.7, or +3.7 to +6, which could completely change the climate, because if we lose, for example, AMOC, the Atlantic Meridional Overturning Circulation, maybe the climate of Barcelona and Bordeaux could look a bit more like the climate of Quebec in the winter, which would change many things, including my wine preferences, probably. So this, what I wanted to say about that is that there's a lot of research in climate science about that. There's also some research in green finance. And recently, there's an excellent paper by De Angelis and Peter Tankoff, who investigated the green paradox and the fact that human behavior, in particular fossil fuel extractors and investors, could be somehow very bad just before the tipping point is reached, which could somehow trigger the reach of these tipping points even a few years before. And with Ansgar Galbrecher, we also are working on a paper about how to include those tipping points in the design of stress test and in somehow the analysis of climate change risks in actuarial science. Why do I end my part of the presentation on that? This is because I think that to address a bit further this preliminary study that Eric will present, probably actuaries also need to work more and more with climate scientists, because we used to work a lot about extreme value theory or about with our past claims data sets. But more and more now we are shifting into climate models with forecasted climate and simulated insurance claims based on these future climate simulations. And when I attended a conference in Brazil last summer, we could see that there was a big discrepancy between the results of the 30 plus climate models that are used in the IPCC framework, for example, and that for some risks in Brazil, at least 29 of those models did not capture very important components of what is listed here as Amazon rainforest special risks, and that could prevent somehow actuaries who would use those 29 models to assess and to manage climate risk in Brazil in an appropriate way, because the model wouldn't even have the right ways around, depending on some climate cycles. So I think that's a great research direction for the world profession, but also a big challenge to be able to get robust enough decision making based on this new paradigm. I just let Eric now present you the agenda of the rest of the.
Thanks, Stéphane, for this very nice introduction about what happens when you get close to an alpha of one. Okay, so coming to some more quantitative elements. So first, I'm going to describe the database which is used, and then how you can fit GPD parameters. It's most of you will know that. And then we'll come to the projections of these parameters. And finally, based on that, we'll see how we could apply that in, I would say, day-to-day work for practitioners like me, actually. Okay, so the database of which was used is the EM database from the, if I'm not mistaken, the Université Catholique de Louvain. So it's a database of historical database of international disasters. You can download it freely, so that's very nice. And yeah, it records it records disasters that happen in the future and which have one of the criteria shown here. So there were 10 fatalities or 100 affected people, a declaration of state of emergency, or a call for international assistance. So then this database also includes earthquake, it includes flood, it includes a lot of things. And here you see that there was a selection because, of course, we're talking about climate change, so earthquakes were not taken into account, but drought, flood, storms, wildfires. And you can have events going back to the 19th century, if I remember correctly, but I just used from 1945. And only the events with total damage adjusted, which was positive, is selected, of course. And 3 unusual events, I would call that, so were taken out, which is Katrina, Andrew, and the Yangtze flooding on 1998. You will ask me, why did you exclude that? Actually, somehow these events happen too early. And they kind of put the time series of NatCat events. There are tipping points. We were talking about that. There are kind of tipping points which are not very nice if you want to have something smooth. But smooth in the case of NatCat is not easy to decide. We are going to talk about total damage. It's not loss damage. It's the total economic damage, and it's adjusted for inflation. Okay, so Stefan mentioned the fact that if you had an event which happened in the 60s and you compare to now, of course, the improvement of construction, all of that, or the change in the population living in certain areas is not taken into account, but at least inflation is taken into account. Yeah, and I want to mention that the provider of the data says that before 2000, be careful, but well, you need to use what you can. So we used things from 1945 till 2023 or 4. Okay, so this is how the losses look. So this is what we're going to do is use losses above. It's not 200,000, it's $200 million. Sorry, there is a typo here. And you can see that, yes, in this case, when you see the aggregate and you aggregate all the individual damage above 200 million, then you see that there is a trend that in aggregate it goes up. And the database looks like this. You have, say, a year of occurrence. I didn't put the name of the damage, but in 2017 it could be Harvey or Irma or Maria, and then it tells you, okay, that cost 200 million, 135, etc. The database contains 2,049 observation, and what we're going to do is fit a GPD parameter to these observations by sections of 3 years. So fitting a GPD parameter, that's fairly easy. For those of you who use extreme value theory, you know that theorem, which in a nutshell says that the excess of loss above a certain, the expected value, the distribution of excess of loss, they should converge to a GPD distribution, which is a very nice feature of extreme value theory. And what is even more interesting is this last point below, that the expected value of the excesses actually is linear with the excess. So what we're going to do is use this last equation to try to find the parameter xi, which is the inverse of the alpha parameter somehow for GPD distribution. So yeah, the thing is, we have a distribution, we have a list of damages, of losses, and what we're going to calculate is this En of u, which is just the average of each of all the damages, of all the excess, of all the excess compared to u. And what we're going to start, we are going to start from u being 200 million and increase by a certain amount each time. And here you see how it's calculated in some details. So you see the u, 200,000, 400,000, 600,000, etc., etc. You have your cat number from 1 to 19 here, but you have 2049. you have your year of the year when it happened, and you have the total damage adjusted, and then you can easily calculate in Excel, of course, based on the excess that you have here, the average or ENU. And what should happen is that this list of expected loss, expected value should be linear in a U. Okay, so easy to do. And when you do it, you have a slope, and it goes from 200,000 to, I think, 7 billion, 200 million to 7 billion. And in that area, that you have this property of ENU is working, and you have the slope, and the slope increases. Okay, so we are happy with that the theory works. And then once we have the slope, which we can calculate for each year, maybe I should mention that the years which you look at are 1966, 1969, etc. It goes by years or by element of 3 years, okay? And each time, so you have more losses because you know you have more catastrophes in your database which come in. And as Stefan was saying, well, we see that effectively the return period of certain events is decreasing. That's exactly what this graph would say. Okay, so now we can calculate for these different years the alpha. And then we can look at the shape of this alpha per year. And this is where things starts to be interesting, because as you can see, it's decreasing linearly. And I must tell you, when I did that, I was really shocked or surprised, because I would have assumed it would have more bumps or going up or down, but really here it's really linear, which is somehow frightening. And if you project that with a slope of 2.9%, well, actually, you can see that the alpha is going to be above 1 until the year 2051. So after 2051, as Stefan explained a bit before, we will have infinite mean. And it means that somehow, if you look at what I was telling you before about extreme events and giving a list of things that happen, the more it looks like the trend is going to worsen and worsen, and maybe in 2052 we are going to have really, really, really extreme events and things which we didn't expect at all. Yeah. Okay. Now potential applications. Well, easy. You can calculate the expected value for any priority, and you can calculate a factor. By the way, a -1 is missing here, but okay. And then you will see that, for example, I'll give an example, but you should have an inflation, or I will call that a climate change inflation. Say in 2030, you should have 2.9% more, say, premium to cover for climate change if you are covering a property risk. That's what it means. The thing is, because it's a Pareto distribution, of course, it's exponential by nature. And what happens, what I would say, what happens nowadays is, because we are in the range, if you look at that, until 2035, 36, in the range of 3-4%, we don't feel it if you're doing pricing in reinsurance or in property risk, you don't really feel that. You don't know how to implement it. But when we'll start to be, and if it's correct, okay, always be a bit careful. But starting, say, from 2040, we're going to start to have fairly high increases in terms of price if you apply this inflation index. And yeah, it's going, but of course, when we reach 2050, it will be just unbearable. Yeah, so that's something which is a bit is fairly worrying. Maybe everyone should think about, when do you retire? Look at the time and see if you're going to be still okay or not. But yeah, the future doesn't seem so bright for pricing of property risk, or not yet. We can do the same for capital requirement with the same amounts. Again, you have some kind of inflation factor, but it's for the value at risk at 99.5%. Yeah, so maybe some conclusion. It seems to, based on this database, and if you work for a big reinsurer, you may have better data, even though you need to have data for a very long period of time to be able to do that kind of model. But based on that, it's possible to kind of predict a time where climate is going to be really harsh. Of course, it's going to affect insurance companies, but not only. I would say it's possible to adapt premium and capital requirements based on this inflation factor for this change of alpha. I would say that most likely, because climate is not linear, and here we're talking about something which is linear, we are going to see bumps in the premium element in the future. It's not going to be that linear, but maybe it's going to be like that. What you see is that it's going to be very costly. If you see again the series of pricing factors. And the final issue I would like to mention in the IPCC report, and actually whatever we do now to limit climate change, like going towards electric cars and things like that, anyway, the first effect will happen in 20 years. So unfortunately, I would say the future is fairly known. And yeah, we are going to have to face this increase in losses, actually. And that's it for the presentation. We have some minutes for questions. Yeah.
Okay, thank you, Stefan and Eric. So yes, we have received many questions, and some of them are already answered by Stefan, but I think it's we can go through them again. I'll read out questions. So the first one is, which tipping points are of most concern currently? And Stefan, could you respond?
Yes, so thanks for the question. I think it was yeah, so I don't see the question. Yeah, it was from John. So yeah, my answer was I was particularly concerned about AMOC that I mentioned earlier. And in the discussion, maybe I can continue, Ryu. David Wilkie said that for him, sea level rise was the most concerning phenomenon, and I agree that. And my answer to David was that not only it can have impact, of course, on coastal flood, but it can also worsen some other perils for which we don't really immediately see the impact of climate change, and I'm thinking about earthquake risk. We had a roundtable at the French Insurance Federation last year, and there was some earthquake scientist from the southern of France, and he was saying that the primary impact, the direct impact of climate change on earthquake risk from a purely physical point of view was not really material from his point of view, or at least he thought there were some limits that were preventing this risk from being affected too strongly by climate change up to the current knowledge in this field. But he was mentioning that the associated potential tsunamis that would be created by earthquakes could go further inland due to sea level rise, and that in fact maybe some regions are not necessarily protected at the right level anymore by dikes due to the combined effect of sea level rise plus this potential tsunami effect. So that's right, that it's also an important phenomenon. I don't know if it classifies directly as a tipping point, but it is associated to a tipping point, which is the melting of ice in the Arctic. And so I think that's why David related this in a relevant way to tipping points.
Thank you, Stefan. We have about more than 10 questions, so maybe
okay, shorter answers.
Short if we don't have time, we will post Q&A after this presentation on IAA website. So, but let's do it as much as possible. So the next question is, wouldn't it be more logical to consider a worsening of alpha and D parameter at once? Presumably they shift together. If understood correctly, by considering both separately, you find tipping points for alpha and D separately, while keeping the other constant. If considering together, you could determine a tipping line in the graph alpha versus D, couldn't you? So
yeah. So I can answer that one as well because I already did. So usually in mathematics, related to my 2015 paper, when we have 2 or 3 or 4 parameters, we first try to have only one by one changes in order to see what happens more clearly. But it would be possibly I think it's possible to have a look at the simultaneous increase or worsening. For the part of the study that Eric presented, yeah, it's a key question to determine whether it's due to a change of D or alpha. But looking at the slopes that Eric produced, it seems to be due more to worsening of the alpha.
Okay, so the next question, it seems to be that rising sea levels are not the most important adverse effects of climate change. There is no past history of this except many thousands of millions of years ago. But rising sea levels would be worldwide and not reversible. They could have catastrophic effects on coastal regions, and it should not be difficult to get.
Yeah, you already somehow mentioned this comment and question by David. Maybe we can go to David's follow-up question or remark, which is, I don't think skeptics will. Go ahead.
I don't think skeptics will believe in climate change until Venice has to be totally abundant. So I recommend going to see it while you can. It's very humor, a lot of humor.
Yes, I also recommend to go to Venice, but this echoes to some opinions that I heard in France that some people maybe can cope with climate change at the beginning, and there is some belief by some stakeholders that some symbols like Venice or like some French cheese or French wines for us in France will be some strong signals that will somehow make skeptics realize that something has changed. I'm afraid in that case it might be a bit too late to react because, as Eric showed in one of his last slides, everything will be already determined.
Okay, thank you. So the question to Eric, in the preprint of your paper, you also mentioned adaptation measures are as a potential solution to preserve insurability with this specific example of Japan. Can you elaborate on that here?
Yeah, actually, that's a very good question. The point is what happened in Japan, as much as I know, is that what you see is that there was a huge investment by say public authorities generally in the water, in how you say that, in rivers, in making sure that rivers would not overflow, would not make flooding. And actually, when you see, you can have the graph shows that you see the amount of investment and the reduction of the level of flooding, for example. So somehow there is hope in the sense that if public authorities, or yeah, let's say public authorities in general, but also private people, would invest and put a lot of say investment in preventing flooding, preventing where hail is not possible, but most likely flooding, or for storms, making sure you have dikes, I think you call that like that in English, so that you don't have the water which would surge. Then you can really, well, at least based on the example of Japan, and up to a certain point, you can really limit the impact of some natural catastrophes. I hope I answered the question.
Okay. So the technical question, when fitting the GBT parameters on 3-year windows, how sensitive are the results to the length of that window? Would 5-year or annual windows change the conclusions significantly?
If you do 5 years, for sure, it would not change the conclusion, because you would see something fairly similar. If you go to 1 year, I didn't check, but I guess you would have the same kind of conclusion with a bit more of volatility. But I must say I would have to make the calculation. Yeah, again, with 5 years, if you have a longer period, then the conclusion will hold. If you have a smaller one, you may have more volatility, but the general pattern will stay, I would say.
Okay. So simple question, is end of times the end of viable insurance markets?
Good question. I'm an actuary, so it hurts to say that Yes, it's. I mean, what if again if this holds, then I guess starting from, say, if you look at that pattern, starting from 2040 at least, the premium, the problem is that you would have to increase premium, okay? And at a certain point, I guess clients will say, sorry, I'm not paying for that. Or maybe what's going to happen, like I think that's in Florida, the insurers will just go away from some regions, and then people living or having a house there cannot get insurance anymore. That's what we already see, by the way. I think it's in Florida, and this may happen with time, that insurers will say, no, it's not possible anymore to insure properties in this region just because the risk is too high. And if you go, of course, to year 2050, then things are going to get worse and worse and worse. And well, we are in 2025. It's difficult to say what's going to happen in 5 years. So in 20 years, it's even more. So I would say that at least in a first step, I can see insurers, and in particular reinsurers, just pulling out of some regions or some areas in some countries just to say, sorry, it's not insurable anymore. Yeah.
Okay. Okay, so next question. Why did you decide to exclude outliers like Katrina or the young floods? Could their exclusion underestimate the tail risk?
Yeah, that's an excellent question. The issue was that if I would have, as much as I remember, if I had included that, then I would have a blip or a discontinuity, say, in the calculation. And as I was trying to mention, my guess is that because as Stefan said at the beginning, you have a lot of volatility on NatCat, and here we're looking at extreme events of extreme events, and my guess is that these events they arrived too early in the period that we are looking at. That's why they would create some, well, in the time series, then they would create some discontinuity, which was not nice. So I decided to exclude them. But again, we're talking about 2049, 2000 losses, damages, and I just excluded 3 out of them. So it's okay. That's something we can discuss, or maybe there are things to do around that. Yeah.
But Eric, we can also say that in the final version of the paper, there will be this sensitivity analysis.
Yeah, that's true. Yeah,
tests
absolutely.
to check that whether Claudia's point, which is very good, whether the conclusions are completely changed or slightly modified. But it looks like it will just create some not some noise, but some spikes that do not change the general conclusion.
Yeah.
Okay, so next question. Did you try out nonlinear fit for the evolution of the parameter alpha over years?
No, I mean, honestly speaking, bon, looks like a line, really. Unfortunately, I could say also. No, I didn't try.
Yeah, this if I complement as well, I guess the question is logical, because if we continue this straight line, it will start to be negative after some point. So so it's clear that at some point the linearity will be lost, and that there will be a kind of power version or some convex function, some convexity that will come at play. So that's part also of the discussion that we are adding at the end of the paper. But yeah, as Eric says, we have no sign of convexity at this stage. But we know by theory that it will come at some point.
Okay, so the next question is more for the clarification. Does it mean when any tipping point is triggered, the model will need to be recalibrated and the cost will be much higher than what Eric showed?
Yes, that's the thing, that if you have an extreme event, then the alpha goes down immediately. And if it goes down, the cost go up, yes.
And to complement also, in the case of tipping change in the sense of climate change, then it can be interpreted as a different regime. And so there, in addition to what Eric mentioned, the fact that the re-estimated alpha will go down, it might go down permanently, or at least the new events could look completely different in the new regime. The speed at which premiums would be updated and the speed at which reinsurance markets would react, this is a very complex question.
For sure.
Okay, so next question. I understand the calibration was made to total losses, but exposure has also increased. For example, in Florida, how would it look if the calibration was made to weather data such as precipitation?
Well, on the first part, which is the fact that there is more value and etc. in Florida and elsewhere. That's true, as I mentioned, that the inflation was taken into account. The general change of, say, population living in the different areas, and even construction standards being improved. This is very complex to take into account, so that was not done, unfortunately. I must say it would be very difficult to take that into account. But well, yeah, if with time maybe, but that would require a lot of external information. As for precipitation, I must say I didn't understand if we use precipitation as exposure. I'm not sure.
Yeah, I think the idea of Andres is to, I guess that his idea is to say, okay, because the exposure and the accumulation is not stationary over time, it could be interesting to replay the claim or the event thanks to a precipitation-based loss model. So yeah, that would pose other challenges. I agree.
Yes.
But yeah, again, in the final section of the final version of the paper, this is, if we come back, maybe Eric, to one of the caveats that I listed, maybe slide 10 or something like that.
Yeah, sure.
Yes, thanks. It's the point about as if claims. Okay, so it's point 4. And it's true that the same hurricane, the order of magnitude that practitioners classically report is that the same hurricane that hits Florida 20 years after the first one would cause basically twice the amount. So it's an order of magnitude that we're going to use again for a sensitivity analysis in order to compare with discard with inflation and check that the conclusions remain more or less the same.
Okay, thank you very much. So it's time. So that will conclude today's session. Thank you once again to our speakers, Eric and Stefan, and to all of you for joining us. So if you have additional questions, yeah, please send the questions to the email shown in the slide. And also, the questions we couldn't answer will be posted on the IAA website, as I mentioned. So thank you again, everyone, and have a good day or have a good night or wherever you are. Thank you very much. Yeah.
Thank you.
Thank you.
Bye-bye.
Bye.